Good afternoon, dear professor. My name is Lê Anh Đức and this is my groupmate Đặng Minh Hiếu and Phùng Thu Ngân. We are from Vietnam. Today, we are very happy to present our studies with the title Fabrication and Research on Thermomagnetic Materials Applied in Refrigeration and Environment-friendliness. To commence with, we are going to mention the introduction. Firstly, perovskite without doping will make the anti-ferromagnetism dielectric properties. In an opposite way, with doping depends on ion and doping concentration. The crystalline structure of electrical and magnetic properties change significantly to produce the emergence of several physical effects. Then, the anti-ferromagnetism will experience an amendment in the ferromagnetism by doping different elements.
While many research groups to implement to dope transition ions Ca2+, Ba2+, Sr2+ into a Ca. Subsequently, substituting La with Nd in the material system, La1 - X, Ndx 0.7, Sr 0.3, MnO3. X equals 0, 0.2, 0.4, 0.6, 0.8, and 1.0. So Tc and delta Sm mark modifies delta Sm mark, which is 4.38 Joule per kilogram Kelvin. All of them honor a vast magnetic caloric effects. To put on a cell in this part, we can see obviously that this study brings about the creation of single plate system. La 0.5, Md 0.5, 1 - X, Srx, MnO3. X equals 0, 0.1, 0.3, and 0.5. And the evaluation of structural properties and modification of magnetic and magnetic caloric property via volatility of doping concentration.
Now we briefly talk about experimental. The symbol La 0.5 and E 0.5, 1 - X, Srx, MnO3 were fabricated by a solid phase reaction of the oxides La2O3 and Na2O3, SaO, MnO. The symbol is preheating at 1000 degrees C in 10 hours and annealed at 1250 degrees C in 10 hours. The symbol after manufacturing are measured the crystalline structure and magnet-to-caloric property.
Now let's move to the main part of our presentation, results and discussion. By watching the XDR in Figure 1, we can see that samples are single-phase, suitable for cubic crystal structure. We also can calculate the average of crystal by using giant biscalar equation. Figure 2 is magnetization depends on the magnetic field. When X increases from 0 to 0.2, the samples are paramagnetic. When X increases from 0.3 to 0.5, the samples are ferromagnetic. Moving on to Figure 3 is magnetic dependence on temperature of the sample system and differential form of magnetization, dm/dt in Figure 4. From MT curve, we can calculate the kappa minus 1 and kappa. The Curie temperature was determined and solved in Table 2. When X increases from 0 to 0.3, the Curie temperature significantly rises, but when X reaches 0.5, Curie have a downtrend. It's clearly that X equals 0.3 is the best samples. We got the highest Curie temperature, 295 Kelvin.
From empty curve, we can determine kappa T and kappa minus 1T of the sample system in Figure 5. In Figure 6 is family of isotope magnetization curve and entropy variation of the sample X equals 0.3. As we can see, the highest fluctuation of magnetization is between 287 Kelvin and 308 Kelvin. So we can determine the highest Curie temperature is about 295 Kelvin. The transformation in linear shows that the higher changing entropy, the higher changing delta S. And delta Sm is one of the values that refrigerant or cooling. Finally, I would like to conclude that we have succeeded in preparing perovskite single plates by the simple cubic crystal structure. Sr2+ impurities increase from 0 to 0.3. Tc on delta S mark decrease when X equals 0.5. Optimal doping concentration of the sample system X equals 0.3. Furthermore, the materials can be applied in refrigeration, environment friendly, and having high economic value.